So we are doing another tutorial for Nastran Solution 200. This one's slightly different from the previous ones because this is actually a built-up structure. My name is Christian Aparicio and I will be walking you through today's example. So here's our goal. I just mentioned that we are working with this built-up structure. It's basically a flat plate, if you will, with this beam here that will add some stiffness. And this is our goal. We are going to vary both the thickness of the plate and the thickness of the beam cross section. So by the end, we're going to go from design on the left to the design on the right. We are doing this so we can go ahead and minimize the weight from 6.962 to a new value of 5.484. Now, before I go into more details regarding this example, it would be worth describing how this model is configured, how is it loaded, and so on and so on. I will then cover the optimization problem statement. This is essentially a requirement for optimization. This problem statement is composed of your design variables, your objective, and your constraints. Once you have this summarized, I'll then teach you every step you need to take in order to run this in Nastran Solution 200. After we perform the optimization, we'll go ahead and look at the results. And then at the very end, we'll update the original structure with the optimized parameters. Now, before I go ahead and start, just in case you are a professional engineer and you are watching, if you have any questions regarding training, if you have any questions regarding how to use Solution 200, or if you have any other structural optimization related questions, you can contact me at this email address and I would definitely get back to you. Now, we are going to use a very special tool here called the Nastran Solution 200 web app. If you're a student or engineer, you can also get access to that by contacting me at this email address. This example is from the MSC Nastran Design Sensitivity and Optimizations User's Guide. You'll find this example in Chapter 8 under an example called Stiffened Plate. So if you want more details regarding this example, I definitely encourage you to refer to this documentation. Now, we are using line and two-dimensional elements for this structure. So on initial sight, it may not look like a built-up structure. Trust me when I say that we have assigned properties to these one-dimensional and two-dimensional elements. So the structure actually looks like the one shown in this diagram. Now let's go ahead and talk about the load cases. We have two load cases. In Nastran terminology, the load cases are usually called subcases. So for subcase 1, we have a pressure distribution applied to the plate. We also have a running load here on one of the edges. We also have a second load case where we're applying a point load to a node in the plate. Should also add that each edge is simply supported. Now let's go ahead and talk about the optimization problem statement. One thing I want to point out first is our first design variable x1. This is going to be corresponding to the thickness of the plate. So you can imagine here in red arrows, I'm defining the thickness t. This will be our design variable x1. We will also impose these bounds on what the thickness can take. The second design variable will be the thickness of the beam cross section. So this will be design variable x2. You'll also notice that we are going to use the same bounds. One other thing to keep in mind, I don't know if this did a good job or not. When you're defining your beam elements or your beam properties, there is something called an offset that you specify. So here, for example, this dotted line represents what the offset is. So I'll call it OFF. This offset is carefully specified in order to prevent this scenario that you see here. if we zoom in and look carefully, we see that there is actually an interference if the offset is not properly set. The existing finite element model is okay. So here you can see that there's no interference. So the offset for this example is essentially okay. But keep in mind that since the thickness of the plate, so that would be this dimension, since this thickness will vary, it's going to invalidate the offset that we constructed prior. So we are also going to express a new relationship for this optimization. We are going to say that the offset is equal to the thickness of the plate, or rather dimension 1, which is the thickness of, let me see here, dim 1 is actually the height. So what we are going to say is we are going to take half the height, so from the top to the bottom of the beam cross section, we're going to divide that by 2. So that would be this term that you see me double underline. And we're going to add it to half the thickness of the plate. So here you can imagine this is T. We're going to divide it by 2. This is going to give us this thickness. And then we're going to add it to this offset that you see here. So then at the very end, we're going to end up with this new expression, 1.5 plus x1 divided by 2. This is going to be a special relationship we have to define to ensure that there is no interference between the beam cross-section and the thickness of the plate. Now we just covered the design variables. Let's now talk about our objective and constraints. Your finite element model, when it's evaluated, whether you're performing a static or normal modes analysis or some other type of analysis, it's going to produce a lot of responses. So for example, weight, volume, displacements, element strains and stresses, the list is very long. This is where you single out which values will be the objective and which values will be the constraints. Now, as for the objective, we are going to say that the response known as weight will be the objective. We want to go ahead and minimize the weight. And now what about our constraints? Here we are going to impose stress constraints on the beam elements rather. Here what we are going to say is that for this one beam might span from here to here. So let me go ahead and make sure I specify that here. So here you can imagine this is your beam element that I'm defining here. There is going to be an end A and then an end B. This is the line or beam element. You're not seeing the cross section projected on this line element. What we're going to say is we want to constrain the maximum stress of end A. And then we're going to create a second constraint called the maximum stress at end B. Now, here in this top right-hand corner, I have an example of what this constraint might be. So here, if we take the top face as point A, when we look at this and we look at what the maximum stress is at end A, we see that the maximum stress out of 2.25, 4.95, negative 2.25, and negative 4.95, the maximum stress at end A is positive 4.95 megapascals. And that's what this maximum stress at end A signifies. If we have a stress distribution like this, we're just taking the maximum stress quantity. We're going to do this again for end A and end B, not only for element 1, but we're going to do it for element 2, element 3, and element 4. So this is a good point to bring something up. We're going to define the stress quantity R1. This is going to be applied to 4 elements. So 4E, if you will. So even though we've defined one constraint, if you will, it's actually constraining 4 elements. This R2, even though it's one constraint, it's actually constraining 4 elements. Here we're constraining the stress for ends A of elements 1, 2, 3, and 4. Here we're constraining the stresses for end B of elements 1, 2, 3, and 4. Now, what about the plate? What stresses are we interested in constraining here? We want to constrain the von Mises stress. So we'll say that the upper bound of von Mises stress is 25,000 units of stress. We want to do this for both the top and bottom fibers of this plate. So here you can see from this diagram, the top is this side of the plate and the bottom is the opposing side of the plate. This, like before, is going to produce numerous constraints. Even though we've defined one R3 constraint, since there are 16 elements for the plate, we are going to constrain the top fiber stress for 16 elements. So here I'll type in 16E. And we are also going to constrain, even though we have one constraint defined here, we're going to constrain the value for 16 elements, specifically the bottom fiber. Keep in mind that we're not going to click 16 times throughout the web app. We're just going to create one R3 constraint and one R4 constraint. But know that in the background, there are 16 elements that are being constrained for the yellow plate that you see here. The other thing we are constraining is the Z displacement for two nodes. So here, I think this slide is pretty self-explanatory. You can see that we're going to constrain this node for R6, so that would be here. And then we're going to constrain this node for R5 using these bounds. One thing I want to point out is that since we have two different load cases or subcases, we are going to apply the constraints differently for each subcase. Our 4 stress constraints are applied to both load case 1 and load case 2. But the R5 displacement constraint is only applied to load case 1. The R6 constraint of displacement is being applied to only load case 2. R5 and R6 we just previously discussed on the previous slide. So here's a quick snapshot of the entire problem statement. Remember, always have this prepared before starting your optimization procedure. So now let's go through the process. Step number 1, obtain the BDF file. Here, the BDF can come from two places. Number 1, you went ahead and constructed your own finite element model using your own pre-post processor. Here, for example, I've gone ahead and already built up the structure. If I wanted to, I can go ahead and open the results because I've already gone ahead and performed an evaluation here. And here I'll go ahead and plot this just to prove to you that this model has already been constructed. So this would be your starting point. You've already gone ahead and created your BDF file as I'm showing here in this directory. Now, if you want to follow along with this example, you can open the web app and go to the user's guide. If you go to the size optimization tutorials, there's an example called automated structural optimization of a stiffened plate. Right click on the starting BDF files and click save link as. We'll go ahead and save this file to my desktop. So on my desktop is the same model. You can download this file and follow along. This file includes the entire stiffened plate. It includes the materials, the loads, the position of each node, all the elements, and so on and so on. So this is one single file that now must be converted to solution 200. So now we can move on to step number 2. Remember the optimization problem statement? We've explicitly defined what the variables, the objective, and the constraints are. We can now construct this for Nastran. So to do this, go back to the web app and click on the size icon. This is going to open the web app we use for the tutorial. I'll go ahead and select the BDF or DAT file we just downloaded. This is where I can go ahead and search all of these properties for the thickness property. I can then go ahead and set this as a design variable. And here I believe I said that the design variable is allowed to range between 0.001 and 10. We also want to set the thickness of the beam cross-section as a design variable. So here I want to set the dimension 2 as a design variable. And here we're using the same lower and upper bound of 0.001 and 10. Now, let's take care of creating that special relationship in order to prevent any interference like I mentioned a few slides ago. Remember, if the thickness of the plate increases or decreases, it renders the previously created offset outdated. So we have to make sure that the offset is properly updated during the optimization. So let's go ahead and work on that now. Remember, the expression is 1.5 plus x1 divided by 2. So if we scroll down a little, or rather scroll up, delete this and look for something called W3. These W3s are what specify the offset for the beam elements. So here, let me go ahead and click on options. I'll mark the checkbox DVXREL2. This does one thing. It produces a new column here in this table. When you click on a plus icon in this column, it adds that property to this new table. In this new table is where you can specify equation relationships. So here, we're saying that 1.5 plus x1 divided by 2 is going to update the offset for us. X1 is the thickness of the plate, and you can tell because the label column says that it's X1 that corresponds to the thickness of P shell 1. Now, instead of clicking on each of these icons individually, what you can do is type in the expression in this other box. And then when you click on this bulk create icon, it will mark all of the visible plus icons automatically for you. So here you can see that it's clicked all of these, and if I scroll down, it's gone ahead and used the equation I specified in the box above. So that essentially concludes creation of the relationship. One other thing you might want to consider doing, let me see if I have the notes here. Or rather, I'll skip that comment for now. Let's go ahead and focus on the objective. The objective is pretty straightforward. We want to go ahead and minimize the weight as much as possible. And now let's move over to the constraints. I'm going to go through this very quickly just because I've demonstrated this multiple times in the previous tutorials I've done. So here I'm going to look for stress. I'll go ahead and create 4 stress constraints. And then I'll create 2 displacement constraints. So the first 2 will be applied to any elements associated with P bar L. What was the idea again? I think I have this specified in my optimization problem statement. So P bar L3. So let's go ahead and type in 3 here. The next 2 stress constraints are applied to any element associated with P shell 1. And then here I want to constrain this first stress constraint for end A maximum. And this one would be end B maximum. And then for P shell 1, this would be the top fiber. And then this next one would be the bottom fiber. And then the top, or rather the upper bound, will be 25,000 psi. And we'll use the same value for the other stress constraints. For the beam stress constraints, we want a lower bound of negative 25,000 units of stress. And now for the displacement constraints, we are constraining this in the Z or T3 direction. R5 corresponds to node 10302. And the next grid is 10203. Now for the lower bound, negative 0.1 and positive 0.1, negative 0.03 and positive 0.03. So there we go. We've gone ahead and created all of our design constraints for this example. But now we have to assign these constraints to the load cases or the subcases. So here, if I go to the subcases section, this is where I can go through my assignment. First thing we want to do is assign all of these constraints to all the subcases. So I'll mark the checked visible boxes. But then we want to leave out constraint R6 for subcase 1. And for subcase 2, we want to leave out R5. Remember, a few slides ago, I mentioned that The stress constraints are assigned to both load cases 1 and load cases 2. R5 only belongs to load case 1, and R6 only belongs to load case 2. So now that the constraints have been assigned to the load cases, we can now export the model and perform the optimization. So let's go ahead and download this new zip file, extract the contents, and double click start MSC Nastran to perform the optimization. Now, while that's happening, it's important to note that here on the right is the BDF file that's been converted to Solution 200. Here on the desktop is the original BDF file. If you hold these side by side, you'll notice so many differences between the two. Before you were performing a Solution 101 analysis, the web app has converted the same file to Solution 200. In addition to this, in the second file is a summary of all your design variable statements, all of your constraints, your objective, everything that's needed for the optimization has been provided to you. After we're done with the optimization, the web app will automatically have the results uploaded for you. Let's read the first and top message. It says run terminated due to hard convergence. This is indication that the optimization has gone through successfully. Here I can see that the very starting weight of this part, or the structure rather, was 6.96 units of weight. By the end, the weight was minimized to 5.47 units of weight. Let's look at the design variables. Here, the thickness of the plate started at 0.15 units of length. By the end, it has a new thickness of 0.11. And here, the same for the thickness of the beam cross-section. It started at a value of 0.1, and it ended at a value of 0.083866. What else would I like to review here? This table for normalized constraints. This one's always worth looking at. So generally, you always want to have normalized constraints that are less than values of 0.003. Any value above the default value of 0.003 means that the design is being violated. So here at the very beginning, we have a negative normalized constraint. That means that our design is currently being satisfied. But since the next design cycle has a normalized constraint value greater than 0.003, this new design that was found is violating at least one constraint. The optimizer works to minimize this value, and you can see that towards the end we get a new value that's very, very small and less than 0.003, and that's when the optimization terminated. Now you might be asking, what are these values representing? These values are actually not representing any specific quantities of your structure results. For example, if I look back at the constraints, we specified stress and displacement constraints. These values are not stress values. They're not displacement values. These are known as normalized constraint values. Now, how are these normalized constraint values associated to the stress and displacement constraint values we specified? Back in the size web app, go to results and click on responses. Let me open this on the left. Upload the F06 file that's in the same working directory where the optimization was performed and upload it to the web app. Click on this icon called maximum constraint for each design cycle. For the initial design cycle, there is this column. The normalized constraint value is negative 1.639. If we look back at the plot for normalized constraint, that's what we have here, negative 0.1639. But again, this is a normalized constraint value. What is this? What quantity, what stress or displacement quantity is this referring to? Click on this blue icon and it's going to show you additional information about this one quantity. Here we see that the quantity corresponds to constraint R1, which is a stress constraint. This stress constraint is for element 34 And if you recall, R1 is the end A maximum stress. And you can repeat the process for each new design cycle. You can see that for the first design cycle, a different constraint governs the design. This other constraint that's governing the design is R5. It's a displacement constraint. It has a value of 6.544. So if I look here, I have a value of 0.6544. If I want details regarding this constraint, I click on the blue icon. And now this is telling me that this displacement constraint is the third or Z component for node number 10302. And here, if you look at each normalized constraint value, this corresponds to the values that are given in the plot. So again, these values that you see in this plot, they're not actually stress or displacement values. They're normalized constraint values. If you want to associate these values to actual quantities, you have to use this responses web app to sort of backtrack and discover exactly where the values came from. One other thing I want to leave you off with, remember that for the R1 constraint, we only defined one R1 here. But if you recall from my discussion earlier, it would be worth looking at this. This R1 is being applied to each beam element that you see here in the model. Specifically, it's being applied to each end A of each element. So what you should expect, at least, is to find more than one constraint when you look at the responses table. Here, you should be seeing 4 element values. So let's go ahead and see what we have here. So here I filtered the table, so I'm just looking at R1. You can see that for design cycle 1, we have 2 R1 values. So maybe it'd be worth doing this. So for design cycle 1, we have 2 R1 values. Let's go ahead and click on the blue icon to look at what these values actually represent. So here, this row corresponds to the stress at end A for element 33. This next value corresponds to the stress of element 34 and A. And now you might be asking, well, we applied the stresses to 4 elements. Why are there just 2 elements being reported here? The reason is because of something called constraint screening. What the optimizer in Nastran will do, it will look at each constrained value for each element. And then it will realize that, okay, some of these values are far from being violated. So I can essentially neglect some of these constraints and just focus on the most critical ones, which might be the ones I just circled. So here, if you look at the beam stresses, it may have realized that for element X or element A, it doesn't need to worry about this constraint. It's too far from being violated. The same for the second element. It's not important. But for the 34th and the 33rd elements, so here 33 and 34th, these are critical in the eyes of the optimizer. So that's why you see that the table is actually reporting these values here. So if I leave this, you notice that not every element is always taking part in the optimization, or not every constraint, rather. If you look at the R5 also, you can see that you can deduce which node, which component was used to produce that quantity, if you will. So here, let's go over one other thing. How do you view your new structural results? If you look inside of that same directory, there's a OP2 file. This is your results file. You might have an XDB file. This file contains both the initial and the optimized structural results. So here, let's go ahead and bring these results into Patron so we can explore them. Let me go ahead and select this OP2 file. And if we look at the results, remember that we have 2 load cases, so we expect at least 2 sets of data. If we look at the data, we have 4 sets of data. each row has a marker, D0. D0 represents the initial design. So D0, you can imagine, is corresponding to the very initial design cycle, if you will. D5 corresponds to the final design cycle. Here, D5, if you look back at the plots, D5 is the last design cycle. So these are the structural results of the last design cycle. So if I look at something like the von Mises stresses, let's go ahead and display those. So von Mises stresses, here we'll go ahead and look at Z2. Always make sure to turn off averaging. And so here, it's always important to inspect and make sure that this is well under the stress constraint. So everything looks good here. What was actually the value? Right, 25,000 units of stress. So these values should always be less than 25,000 psi. So this was for the initial design. We'll go ahead and switch to the next design. So here we have about 23,000 units of stress. What about the second load case, the final design? Here we have about a maximum of 6,000 units of stress. I could do the same for the displacement. Let's go ahead and just look at a simple displacement plot. The reason I recommend going through this comparison of the initial design, then looking at the final design, you want to make sure that visually the results or the constraints have been satisfied. The last thing you want to do is find out that there is a node that is displacing 5 kilometers. That would definitely be an error that can be spotted if you just look at the results very briefly in your pre-post processor. Just keep in mind that if you see data that says D0, that's the initial design, and something like D5, that corresponds to the final design cycle usually. In our case, it was 5. So now what is the last thing I want to show you? Let's see. So we know that we've reduced the weight from 6.96 to 5.48. The last thing, updating the BDF file with updated parameters. So remember, this starting BDF file has old data. It has old data for the thickness of the P-shell entry. It has the old thickness for the beam elements. So this has to be updated. Let me go ahead and create a copy of this BDF. I'll call it updated rather. If you look inside of the working directory, there is a PCH file here. This PCH file has updated properties for any property that was modified during the optimization. So here we see that the value for the thickness of the beam is no longer 0.1, it's 0.08386. And this is the same value that was reported for this design variable, 0.08386. We also have a new thickness. The new thickness is now 0.112735. And now you also see a set of new C-bar elements. Remember that we specified a relationship between one of the design variables and the offset of the beam elements. So the offsets for the C-bar elements have also been updated. So this is data that should also be moved over from the left and copied over to the right. So here, let's go ahead and delete P-shell 1 from the right. We'll delete the old P-bar L entry, and we'll delete the old C-bar entries. Now what we can do is cut all of these old new entries from the left and just paste them here on the right. So here, let me highlight the section so you can see. So we relocated these new entries to the updated version. So let me go ahead and close this. And now if I save it, that completes the update process. This file now contains the updated properties that produce the optimized version of the model. And that is essentially the end of this tutorial. Before I close, just a quick reminder, if you have any questions or comments, please email me. I will be more than glad to give you a response. Also, if you're a professional engineer and you would like more training or if you would like to ask a complex question, you can contact me at this email address. If you are a student or an engineer, you can get access to the Nastran Solution 200 web app by contacting me at this email address. Thank you for watching.